Our next speaker is Rick Maule from Qualcomm. Rick is a senior director in Qualcomm's application processor business, where he works on expanding the role of Qualcomm's DSPs in a variety of applications, including embedded vision applications. Rick's talking about heterogeneous computing, and it turns out that's what our past couple of speakers have also been talking about. Heterogeneous computing referring to this idea of using a combination of different kinds of processing elements on a single chip, typically. It doesn't necessarily have to be on a single chip, but often on a single chip, using these different kinds of processing elements. So Ken talked about CPU plus FPGA in the Xilinx Zynq product. Mario talked about also CPU plus DSP, as well as CPU plus specialized parallel processing engine. Rick is going to bring that into the realm of mobile application processors, which have an amazing variety of processing elements on them, and tell us about how we map vision applications onto that type of heterogeneous processor.
Okay.
Rick?
Thanks, Jeff. For those who don't know me, I'm Rick Maule. I'm with Qualcomm, as Jeff said. I'm going to come at this from two things. One is it's mobile oriented. If it plugs into the wall, we're not as worried about it. The second thing is that I want to, although I'm coming from handsets, tablets, in recent times, the kind of processing that can go on here, and a lot of the different applications we've seen throughout all of this, is going to end up being able to be addressed by exactly either, if not these systems on chips, by others. But you start thinking about any application for embedded systems where you have a pretty highly integrated SoC like this. What we've seen going on in the handset area, as I said before, we've moved from making phone calls and carrying around our music to adding cameras, adding big displays, and we've seen an explosion in applications that people want to write for their phones and people that are embedded into other areas for imaging, enhancing images, etc. That's led to a whole series of new emerging workloads that are having to go in for these various different areas. And as many of the speakers today have pointed out, all of this, when it gets off the camera and you need to now do something with it, is quite compute intensive. But there's a large variety of the characteristics that end up happening in this. And behind all of this, you have a lot of math. If you're doing something where you're calculating things like slip and fits and whatever, there's physics, there's areas of that. A lot of the applications we talked about today was the area of computer vision, specifically extracting information from the images themselves, and then being able to do something with that. Figure out whether that was a gesture that you were looking for. Figuring out how you're going to enhance the image that you just did based upon the information. And then upon recognition of something, the object detection and object tracking, being able to do augmented reality where we put over that. But in mobile devices, we have this constraint of I want to be able to do it in something small and sleek, and I'd really like my battery to last all day. No, I'd really like my battery to last all week. But we got to be able to have the battery life last a long time, even with these very and computationally intensive applications. But the one I'm going to touch upon most in what I'm talking about is this area of thermal efficiency. As we've seen the processor growth that you've seen just in the recent couple of years. We've gone from single to dual to quad-core CPUs. The performances have been below 1 gigahertz all the way up beyond 2 gigahertz now. And we certainly are adding a lot of computation for us to be able to do a lot of these things. But if we do all of this on the CPU, for all the things that we were just talking about, you probably don't want to hold that phone. We've had a number of different places where the promise of what was going on in these cores are bouncing up against their thermal limits, and they're not able to achieve the goals, especially in the areas of imaging and vision. We're just not hitting frame rates that we wanted to do because we're running into the thermal constraints. My key message here is, yes, we've got an incredible amount of processing power that's happening in CPUs. Okay, but we need to figure out how to look beyond the CPU. And in the kind of SoCs I'm talking about, it's because the CPU, even a quad core, If you go up to Intrinsic's booth, showing one of our recently shipping 8074 chips that are on one of their boards, the amount of the SoC that's the central part there, that's the CPU, is only about 15%. The rest of it is a number of other types of processors that are complementing that are around it. The CPUs, GPUs, DSPs, areas in the connectivity. We've had people talking about being able to get out to the cloud. We've had people talking about what driving displays. What I'm really going to focus on for the rest of this is in that upper left-hand corner. You know, how do you end up getting the most out of and balance between the CPUs, GPUs, and DSPs for you to be able to achieve the kind of processing performance you want, but stay within those thermal envelopes. So the key issue here is get the right task on the right processor. You don't build a house with just a hammer. And the reason all these processors exist, they didn't come into existence in the last couple of years. CPUs, GPUs, and DSPs all existed before. They started off in the PC world. They've been moving into this. They've been in the embedded world for lots of applications. Those kind of applications have led them all to get integrated into these complex SoCs that are in the mobile world. We get asked pretty frequently, my compatriots and myself in the application process area, so what's the difference? I'm not really going to end up going into a great deal of detail here for you, but I'm going to give you a slide that will be in the set that you get out there that talks about the difference between application areas you apply them to, what kind of compute control, flow control you can end up doing with the processors, et cetera. Each one of them is very different in their application, where the CPU's primary area is that it takes complex control flow better than any other processor you've got. If you need to turn on a dime in making your calculations, traversing a game tree, figuring out any type of, where you're doing estimations and you want to end up using a table type lookup, nothing's going to be better for you than the CPU. But if you've got something where you want to do the same calculation over and over and over again, and you just want to stream data to it, nothing's going to be better in there than the GPU for being able to do that. And the DSP sits somewhere in between those two. Because of its unique characteristic of being able to intermix control code and data flow into even the same packet, the same instructions that are going on, it sits in the middle, right between the CPU and the GPU, and the types of things it does well. One of the things I do want to focus on is a characteristic. This table will be in your charts. Don't try and read them right now. It's an eye chart. But the characteristics, as you've heard earlier today from people talking about DSPs, most modern DSPs are VLIW engines. Most of them in trying to pack multiple instructions into a packet that all get issued simultaneously and executed by the DSP engine. So the purpose of a DSP is architecturally is to try and get as many instructions as possible done in the same clock tick, issued in one packet that the engine works on in a single clock tick. Unlike a CPU that tries to end up taking those like 4 instructions here and rippling down through them as fast as possible using superscalar and out of order techniques, the DSP wants to try and get them in parallel and get instruction parallelism where they're all going together. And what that ends up doing is that it ends up giving you, why does it keep bouncing? Okay. What it'll do is it'll give you a situation where, and what I did was I picked a bunch of imaging, computer vision applications of what ends up happening in terms of instructions that get packed up in packet. This is the average in running this entire feature for computer vision, for video, for imaging. In a VLIW that's got a good compiler that's driving into it using C, you'll end up getting these kind of instruction packing into a packet that are being issued all simultaneously. Nirvana on a CPU, even doing out of order and superscalar operations, if you get north of 1, you're doing really well. If you get up to around 1.4, 1.5, superstars are working on that. If you have somebody that's programming a DSP for you, and they're getting instructions per packet of less than 2, then you really need to fire that person and go find somebody. They're not even writing good C code for it to be able to find things in the compiler to schedule. A good C compiler today on a DSP will end up being able to achieve north of 3 that's going all the time. And what that translates into for you is that if I can get 3 instructions done in a clock tick, then I can get the same amount of work done in 1/3 the clock frequency as doing it single instruction at a time. And what that translates into is lower clocks are lower power. So you're going to see for the DSP, or for all of these processors, go in and profile them for what you want to end up doing. There's a number of characteristics you'll have here. You're going to see characteristics like this video conversion. There are going to be occasions where the CPU is going to end up being the best in terms of performance. The y-axis, x-axis is the amount of time it takes to do a task. Okay, and the y-axis is the amount of energy it took to accomplish the task. There are some areas where the CPU is going to end up being the fastest at accomplishing it, and as a result of that, lowest energy. Flip side of that is there's going to be other algorithms where the GPU is going to end up doing the same. It's going to achieve the fastest performance and the lowest energy as a result of getting done quickly. The DSP has some areas where it's unique, like in the area of face detection, feature detection we were talking about in some other groups, where in the base of the context, you found something and you now want to, I think this might be a face, now we want to switch immediately to some other algorithms. Well, the DSP can turn on a dime and reapply SIMD or parallel instructions to be able to run the algorithms to look at this candidate and decide, is this a face or not, and then move on to the next candidates. And constantly changing like that, which is not something a GPU would want to be able to do. But notice one thing here, in all of these, the DSP is about the lowest energy that you're dealing with, no matter what the amount of time it took to end up getting the job done. So if you're running up against your thermal constraints, and you're trying to still get the job done, then you need to be thinking about, how do I balance out what am I doing on my processors? Or if the processors are already busy, you know, where do I want to have things go for me to end up having my battery last as long as possible? Developing heterogeneously, being able to use all three of these programmable processors that are becoming more accessible and more programmable today. Well, it's not enough to just have the processors in there. You have to be able to get to them, and you have to be able to program them. So one of the things that you're starting to see out in the industry of anybody that builds integrated SoCs is more programs to give you the ability for you to actually get to these processors and program them, and a tool set to be able to do that. Several people talked about different languages, different APIs that are happening here. OpenCV for computer vision applications. Qualcomm also has an augmentation to OpenCV called FastCV. OpenCL, RenderScript that's coming out. All of these are languages that are becoming available for you to be able to do work in the vision domain. But there's a lot of investment that's going on underneath that. There's a compiler technology. GCC has been around for quite a while for C and C++ areas, generating code and targeting area. But it also has been around for a while, so it's got a lot of baggage and a lot of legacy that's going on. There's a new tool chain that's hitting the marketplace. There's a lot of participants in it, LLVM. That tool chain allows you to do one-for-one basically everything the GCC tool chain could do. But it's a much more modern architecture going into an intermediate representation with a big piece of what it's designed to do is to be able to retarget to these different processors. Start with a language and then target it from the CPU to the GPU or the DSP. And at the same time, it gives you the ability to have a series of tools that all map into the capability. So what does that mean for you? Instead of doing computer vision for a CPU, take it and write code and then retarget it across all of the processors. And why would you want to end up doing that? Because if you do and you spread it out, just in test cases, these are a number of different kernels that you've seen different people talking about during their discussions today. Sobel, being able to do 3x3, the dot product on matrix operations, normal cross correlation. You're seeing not just like if you went from 1 CPU to 4 CPUs, not a 4x. By getting it to the right processor, you're seeing 10x, 20x, 50x kind of improvements in the performance you can get over just running single thread on a CPU. What that means for you is, let's look at like some example use cases of computational camera. We have 2 ISPs. We're doing stereo vision We then send the output of those into the processing complex of these processors. What's going on behind the scenes is the processors are calculating a depth map. Okay, then you can say, okay, the thing I care about is only in the foreground, what you see there in the brackets. Well, the thing I care about happens to be the young lady I'm taking this picture of, and I want her to be very crisp, very focused, and I really don't want the background of anything, so I do a bokeh effect of where I apply in a completely different filter, pixel for pixel, for all those pixels that are back in the background. And as a result of that, all of those end up getting blurred through the filter that I'm applying. Same thing can end up happening on, say I have these two ISPs, and I do a technique that's becoming more and more available on mobile products, is I do a rapid succession of a burst of images that are all at different focal lengths. In the first image, you got a pair of images where the first young lady's in focus, then the second one, and all the way down to the one at the end. And then you can use this same technique of look at your depth map, figure out which ones map to the person that you want to have in focus. If it turns out the maid of honor, the second person in the line, is your heart's desire, and you want to apply a bokeh effect to everything else, pick the image she's in focus, go apply that to the other pixels. The other thing you can end up doing is for every one of them, pick the pixels that are in focus for each of these images, stack them, and you end up with what will be an all-in-focus image. Key point on all of this is it's going into this computing complex that allows you to do all of that behind the scenes on the mobile product. One of our key partners working in the computational care area is Pelican Imaging. They're literally creating a software pipeline that's using all of these processors in cascaded effect. They come out of not just 2 cameras, but an array of 16 cameras. Those go into the DSP for normalization, which is followed by the CPU doing the depth map, followed by the GPU then applying post-processing filtering to all of the appropriate pixels based upon the depth map, and out of that comes a post-processed image. So what do you care? So I'll just give you one example of what kind of impact can end up having with this. The discussion about feature detect that we just finished having with people, if you're doing feature detect, this is measured in the lab on one of these SoCs, run an augmented reality application where you're going to overlay some information on an object, but you got to find it. So you're running feature detect pretty continuously on what's going on. It's been optimized over in the CPU and Neon in this particular case. Then you offload that to the DSP. About 50% of the cycles move from the CPU over to the DSP, which are doing it in less than 50 cycles, 50% of the cycles, because it's a VLIW engine. Okay, it's actually achieving this in a little bit shorter time, but the bigger issue is measured at the battery. You have a 30% reduction on the entire device by moving one algorithm out of the augmented reality application. That's the kind of impact you can have by thinking heterogeneously, profiling it, putting it to the right processor, and getting to the end of this. So the message I have for you is on the systems level, think heterogeneously. Think about all the engines that you got to work with, especially the ones that are programmable for you. At the same time, there's a lot of tools that are available from Qualcomm out on the developer website at QDevNet, developer.qualcomm.com. I'm not going to go down through this list of things. You can go to that website, but all of these are available to you. Qualcomm has moved to the opinion that we need to enable the creative minds that are out there in the industry to be able to go and do things on these SoCs in lots of different application areas that we're not shipping. And so as a result of that, we're opening up SDKs. There's SDKs for the entire Snapdragon as an SoC, SDKs for the Adreno GPU, for the Hexagon DSP, et cetera. Go out to the site, look at what you can do. More importantly, for this particular group, go up and talk to Intrinsic that's up in the demo room. They have boards. They're working with people that are in the embedded space. That's what their primary focus is. For them to be able to take our chips, but apply them in completely different ways, and be able to take all of this software programmability to advantage and leverage it into the embedded systems marketplace. And in this particular case, with the explosion that's going on into embedded vision applications. Computer vision enhancing images that you're looking at, augmented reality, et cetera, et cetera. All the different things you've heard about that we've been talking about today. And I thank you.
Thanks a lot, Rick. Very good.